And when you subtract these, you get the answer for quiz. It's like 9825. So that's our quiz from Tuesday. And that was, I think, a very good exercise. I think everyone did it right. And that's just perfect. So way to go. So quiz. I last time mentioned that I updated your quiz scores on the Blackboard. It was done last week. So next time I'll do it, not this weekend, but weekend after. So in another week or so. So you can check and see what you did. If you didn't check as of yet, how you're doing. And yeah, some scores I did not update because some scores stayed the same. So I didn't touch them. And that's why people asking me, Alex, my score was not updated since like September 1st or so. Well, because it stays the same. So I didn't update it. So you can always see if it changed or not. If it didn't change, it's great. Then you're doing just perfect. So nothing to worry, just to be proud of yourself. So anyways, we had this chapter 3 started, and I guess I'm gonna take a look at the other exercise here in the section where they utilized little tables, and maybe I'll do a group of problems that related to the blood categories. So let me try some problems here, like say exercise 13 that says, what's the probability that someone is not in a group A? So what does that really mean? Well, I guess we should be aware of the story for this exercise so we can be able to, yes, I started to record, but thanks for reminding. Yeah, I already record. So for exercise 13 that says probability that it's not A, you can just subtract probability of A from 1. Looks like it's analogous problem to what we just did for the quiz. So what about P of A then? Well, here they talk about the sample size of 100 people, so we can call it as N. That's what we always use for a sample size, right? And if you're dealing with a group A, which is here, then it'll be 40 out of 100. People will say it's 0.4 or something. So you can subtract 0.4 from 1 and get 0.6. So it looks like for this exercise, you just care about one group, and then you can subtract it from 1. Or on contrary, you could have approached it directly. You could have, good morning, you could have just taken the rest of the groups, such as a B, A, B, and a O, and added all of those elements, and that'd be your 60, right? Because in the group B, there are 10. Here we have 5. It looks like 39 and 6 will be 45. So if you add all of these, you get 60 out of 100. And that's the exact same answer anyways. So either way you do the exercise is fine because the answer is the same. So if you get the same answer, I get so happy I give you full credit. So I'm not really picking if you did it one way or the other way, as long as you do it right. Okay, so negative blood type here is also considered. So what they're talking about now is this negative, and negative blood type appears in each group here. So how many of them out of 100? Well, let me just add. So I get 5 for group A, 2 for group B, right? 1 for AB, and finally for O, it's 6. So that many out of 100, and looks like it's going to be 14 hundredths. And again, I think it's more convenient to just write it as a decimal 0.14, which is better than if you start to reduce this fraction. That's not going to be much fun, and it's not really going to be doing much with statistics, right? So it's some arithmetic, but for all we care, we just need statistics. So it looks like problems here are, again, probabilities, again, fractions that I produce, divide by 100, whatever's in numerator. So let's try one more, like problem number 19 that says one or the other, group AB or RH plus. Okay, so it looks like I need to get a group AB, which is here, right? Or RH plus. So now I need this RH pluses to pull out from every other groups. So we got these here, and now I can write number 19 solution. So that's a probability AB or RH plus, positive. Okay, so we have two pieces to combine. So I'm gonna, out of 100 again, as usual for all of these problems, 100 is denominator. So I put AB is, looks like 4 plus 1, right? It's 5. Or, so I start adding the stuff that is not present here. So I go with O, which is 39. Next is group A, which is 35. And finally, in B, we have 8. So it looks like we just select numbers and add them all together. And if you're not sure how to add these, well, use a calculator. Make sure you get the right answer. So you can put a numerator, there's 5 and 39 and 35 and 8, right? And then in the parentheses, I divide by 100. So you get yourself the answer, 0.87, and this is it, 0.87. So another calculation. Well, it looks like we keep producing those fractions, and that's the subject matter of this entire section. And I guess I'll try to check out the next one. See what's going on when we have the probability of the case when you repeat experiment more than once. Let's see what is going on here. So I'm looking at the case right now when we have the probabilities of experiment that being designed from 2 steps. First step is answering question in the form of true or false. So that's the first step. So next step will be a multiple choice question, and there are 5 possibilities: A, B, C, D, and E. I'm sure you're familiar with these multiple choice exams. So same 5 possibilities for the second answer are also possible when you answered F for the first. So we have this same 5, right? If you answered false, like that. So I just produced a tree diagram, and they actually listed 10 possible outcomes here. Notice that 10 total choices are here because there are like T with A, so it's right there, and so forth. So they didn't go through the tree, but they just listed those 10 possibilities. Well, so they say, what's the probability to get the correct answer if correct answer T and C? So looks like if you know that correct answer should be T with a C, well, there is only one such a selection out of 10, right? So total is 10. And out of this 10, there is only one choice that I care about when both of them are correct, and that's 1 out of 10. That's how we used to do this problem. So the point of this section is to actually do it a little bit differently. The point is not to bother with all of that, because that's a lot of writing. What they do is they find the probability of T. Notice if you have 2 answers, and the chance that you guess it correctly will be 1 out of 2. Analogously, if you have multiple choice, 5 answers, the chance that you guess C correctly is 1. 1 out of 5. Notice that they assume that you have no idea about this question, so you just randomly take a guess. So out of 5 for second question, there is only 1 chance that you will guess the correct one. And please notice that when you multiply 1/2 by 1/5, you get exactly 1/10, which is the answer in here. So the point of story was that you don't have to list all of the possibilities like you did before. You just multiply 1/2 by 1/5. And that's much faster. And that actually works for those examples where you cannot possibly list all of the possibilities. Let's say, why not? Well, because there are usually just too many of them. Let's say you repeat experiment 100 times. So if you start to list all of these possibilities, it'll take you forever. The whole weekend, you will be listing those possibilities just to do one problem, but you can do it much faster just to use that so-called multiplication rule, to just take and multiply these 2 things together. And that's what the little formula they coming up with says. So if you have probability of A, and then you repeat again experiment, and you want to get a B, then it'd be a product of P of A and P of B. So probabilities are being multiplied. That's the formula for this section. Again, if you repeat experiment more than 1 time. I want to say one thing which is a little bit different out of this class. I'm going to teach a college algebra class in the second half of this semester. It's 8-week, the second half, so it's 8-week 2. College algebra, it's MAC 1105, MAC 1105. If somebody needs that class, I recommend you to sign up. And this is a Saturday class. I say Saturday. Well, I'll be able to record lecture. And then if you don't want to do it on Saturdays, it's just a couple of hours, I think 10 to something, 12. So if you cannot do it on Saturday, it's fine. I can let you watch this lecture throughout the week and then send me whatever quiz we had or whatever on it. So I don't think it'd be a very challenging class. And I know college algebra is a class that lots of people that study at the community college have to take, because that's college for college algebra. So I recommend you to sign up, and I guess I have plenty of room on that class right now. So if you want to do that, try to do it this week or next week. So don't wait, because I guess you don't want to wait for too long anyway. So just see if that works for you. Then you can always sign up. And again, I will run it in the same online format. It says the class is in the form of it's like some class meetings in the classroom, some out. So I can do all the class meeting outside of the classroom. So it'd be, I guess, convenient for people, right? So just think about it. So anyways, let me go to section 3.4, the exercises, and continue with more probabilities here. So for example, exercise number 4 that says letter or digit. So I'm in section 3.4, and we're looking at exercise number 4 that says take 2 characters password, and first character is letter of alphabet, and the second is a digit. So they listed those digits. Notice there are 9 here and 1 more, so there are 10 digits. So it's from 0 through 9. When you say, what about 10 or 11? Well, those are not digits. Those are the numbers that are designed from 2 digits. So they're talking about just single digits. And for the first place, it's a letter of alphabet. And when you say, what alphabet? Well, I guess the English alphabet has 26 letters. Of course, different alphabets have different number of letters. Say Chinese alphabet has probably tons and tons, hundreds of letters. So, but I'm sure they assume that's English alphabet, so 26 letters. And since they want to know the probability that you get a particular password, then we can see the total, which is 260 here, because you have with each letter 10 choices for the digit. And then out of these 260, there is only one password that is called K9. So one only out of 260 possible passwords. So this kind of exercise could as well be in the very first section of our chapter that deals with probabilities. So what is the difference in here with those previous sections? Well, because once again, they said you could have done it differently. You don't have to, because you already done the exercise, but I just going over the ideas that you could have done it the following way. So you could have just multiplied the probability of K separately by probability of 9. And for K, letter K is 1 out of 26 letters in alphabet. And digit 9 is 1 out of 10 digits. And if you multiply these two, it'd be exact same as 1 out of 260. So this is the other way of doing problem. And of course, we don't have to do problem 2 times, right? Because they technically done the same exercise twice. Just 1 time is good enough. So you don't have to do same thing 2 times. That's too much, right? But the idea of this section is multiplication rule, and that's what we experiencing in here, just multiplying numbers. So I can see the other exercise, maybe a problem like number 7 here, that talks about defective masks. And they say that they purchased so many thousands of gas masks. So in exercise number 7, out of this 19,218, they say 10,000 and 322 were defective. Oh, like more than a half were defective. They probably had a very good sale on those masks. So many were defectives. That's very, very disappointing. Okay. So in the part A of this exercise, they say, if they select first gas mask, and then they also select another gas masks. So what's the chances they're both defectives? So what's probability that one is defective and another one defective? So I'll multiply, right? And one and the other, we just noticed, we just multiply one by the other. So I actually take that 10,000 and 322 over 19,218 and multiply it again by the same nasty looking fraction, and that'd be the answer, right? Because and means times, so I multiply it twice. Some people can say, Alex, you don't have to enter it twice, you could just square it, right? Maybe it's even smarter idea. So if I just take this 10, 3, 22, divide this by 19 and 218, and actually square it. So how can I square it? I can put parentheses in front of this whole thing. Can I do that? With parentheses. See, it's parentheses only with numerator. Okay, and I can put parentheses with denominator. That's just the way it is. And then square each part, and numerator and also denominator. And you get yourself the answer. So it looks like you're going to have this 0.288 ... So you could get the answer in this exercise just by squaring the same exact value. So once we select one mask and then we select the other mask, and then they say we replaced. So we select one mask and then for some reason we replaced it before selecting the other. When you say, why would we replace it? It's a bad mask. Why do we need to put it back in the batch? So please notice this doesn't seem to make much sense in a real life situation. And that's why they actually have exercise part B for us. They say, it makes no sense to replace. Why don't you just throw it away? Because that's a bad mask. So what's the probability that you select both defectives, but you not replacing the first one? What does that mean? Well, you still have out of 19,218, right? 10,322. So you get this fraction to select first mask. What happens then? You throw it away. It's bad mask. Why do you need it? So when you throw away that bad mask, you no longer have 19,218 because you have already selected one. So your total changed. Your total now is 19,217. You see? And similarly, you no longer have that many defectives because you already selected one and you threw it away, so there is one less left. So you get a 10,321. So you need to multiply these two fractions together and then see what's gonna change if you do that. So let me try to do this. So I'm gonna have first fraction. Maybe I'll put parentheses for just in case. So it's 10, 3, 2, 2. That's the same thing, divided by 19,218, right? But then I put parentheses and multiply by another fraction, and that'd be 10, 3, 2, 1 divided by 19,217. Do you think it'd be much of a difference? 217. I don't think so, because it's really pretty much the same number. But please notice that if you start to consider some more digits, they're not going to be the same, right? So one can say, so pretty much the same probability, 0.288 dot dot dot, but if you start to check the digits beyond first one, they're not going to be the same, because one case it's 6 and the other it's 7. Well, but again, it's still pretty much the same probability, but well, that's the answer of part B. So it is not really exactly the same. It's a little bit different. So you can put this digits farther. So I got this 477 here for the first one. But for the second one, it's 464, right? So this is a little bit different. And then I've got the answer in here. And then they, in the part C, say compare. So that's what we just did. We compared those results, part C. So we saw they're not the same for sure. So what about part D? It says, given a choice between selecting with replacement and selecting without replacement, which one makes more sense? So would you put the defective mask back in the batch of masks and then started to select again, or would you just throw it away because it's defective, has no use anyways? Well, I say, well, it depends on the purpose. If I want to try to get a better masks, then definitely I would throw it away. But if there are some other ideas behind this, then I may not throw it away. So it all depends. But probably you want to throw it away because it's defective, right? So anyways. So it looks like we have these exercises that multiply probabilities, one by the other. And when you repeat experiment more than once, of course, it starts to get more and more complicated because there are more choices. So you cannot really draw the tree diagrams, but we can just get used to this ideas of producing fractions. So let me get maybe exercise 10, one more here. Today, I just want to start this section because I know it may seem to be a little bit different with what we did because we repeat experiments, but a little by little, I want you to just get used to this multiplication rule, which is the one above. That's pretty much all we have here. So in problem 10, they say, in the Senate, 13 women and 87 men. So 13 women, 87 men, and the total is 100, right? So that's 100. That's what they considered. Okay, so if lobbyist for tobacco company selects 3 different senators, so what's the probability they're all women? So what's the probability that we have a woman and a woman and a woman again? So it looks like we'd be multiplying according to our multiplication rule, but we need to be careful. What are we multiplying? Because for the first selection, there are 13 women out of 100 senators, so that one is pretty straightforward if I select the first person. Well, I need to select 3 different women. I don't want to just bring one woman And they'll say, so where are the others? We need 3. We'll say, no, I selected the same senator 3 times. So that's the one that I selected. Say, no, we need to have 2 more. We need different people. So once you selected one of these people, 99 will remain for you to select the second one, right? Because you cannot touch the first one already you selected. So 12 women will remain because 1 woman is gone. So we have only 12 remaining. So that's the next one. And then finally, when I go for selecting of the third one, analogously, I'll have 1 less to select from because we already chosen 1. So it's 98 left. And also not 12, but 11 women here for me to choose. And multiplication rule says, Alex, you need to multiply these 3 fractions just like that. So let me do this. Let me multiply them. So 13 divided by 100. Now I want to multiply it times by another fraction, which is 12. Oh, I don't have to put parentheses. I could just do it like that, right? 99. And then finally times 11 over 98. I love this calculator. It just so nicely shows whatever you need to calculate, right? So I recommend that you check it out, this Desmos. So we have 2 zeros and then 176 ... So when I look at such a probability level, which is less than 1%, actually a little bit more than 1%, I would say that this is unlikely to have such a selection. So somebody probably purposely selected women, because if it wasn't on purpose, then chances of it are very, very low. So I don't think it would happen if you were selecting them at random, right? So looks like before we do the next selection, our sample changes. And that's the key idea in this group of exercises, because after sample has changed, well, you need to make sure you no longer deal with the same fraction, but also change it a little bit. Again, today I just want to give you a first flavor of this, and we'll do definitely many more of these problems next time, because I know they require some time to get used to. So let's try one more, and then we'll return back to something nicer. So how about exercise number 12? It says birthdays that coincident. So in problem number 12, the couple attracted media attention when their 3 children born on different years were all born on July 4. How about that? So what's the probability that a child is born on July 4? So just put 4. Well, looks like out of 365 days, how many Julys 4 in a year? I guess only 1, right? And then again, next child is born on July 4 again. So again, out of 365 days in a year, there is only 1 4th of July. And there's a third child. How about that? Third child also born on the same day. So the next year, again, 365 choices, and there's only 1. Let me see. So you could just cube this. You don't have to re-enter this again and again. Yeah, I could just raise it to the power of 3. So let me get a calculator and get the answer here. So I'm going to put this 1 over 365 in the parentheses, and then raise it to the power of 3. I say, how do you raise to the power? What is that you just clicked? Well, here's the choice for power. A to the power of B. Once you click it, it will enable you to put this in. And also, the number I produced looks pretty odd. I think we already saw this type of notation once. It means that I have to move decimal point 7, actually 8 places. 4, 5, 6, 7, 8 places to the left, right? And when I move decimal 8 places to the left, I have to put so many zeros in front of this tool. There will be 7 zeros. I say, why not 8? Well, because you make one move and then 7 more zeros you put in front. So the actual answer is going to look like 7 zeros. And then this 2, 0, 5. There is no chance this is going to happen, right? Probability is way, way less than 1%. So this is definitely very surprising that this happened in real life, because probability for that is very, very close to 0. Someone can say, Alex, what if I just leave this answer for you like that? Would you accept it? And the answer is yes, because that's the same thing. I understand that this is the same thing, so I don't have a problem with that. But I just want to make sure that you understand what this means, because sometimes people see this, they panic, they shut down computer and run away. Don't panic, please. That's just a scientific notation, people say. That's how calculators give very big or very small numbers. That's all it is, so nothing to worry about. So turns out that in this exercise, we had the answer and we're done with it. So they say, so here we have part A of the exercise done, right? Very, very low. Looks like part B is not really having much to do with part A, but we can still do it. It's a little bit different. So what's the probability that 2 people selected have same birthday? What's the probability for part B that people have same birthday? It looks like out of 365, now I need to say, pick on one person's birthday. Let's say it's 1st of July, or 4th, or 10th, or January 1st. So one person can have a birthday at any day, right? So what's the chances that the other person has exactly the same birthday? Well, one day is booked, right, by first person. We don't care what day it is, maybe January 1st. So what's the chances that second person out of 365 chooses the same day, that one day only? Well, that's 1 out of 365, right? We say, but there are 2 people. Yes, but for the first person, we don't really care what birthday is. What day doesn't matter. We just care about the second person. That's the key idea in this exercise. So first can take any day that person likes, but the second must, out of 365 days, select exactly the same day. It's only one choice. So this is worth to think about, and I know this is not very obvious, and that's why I'd like not to continue with this, because I want you over weekend to give it a thought. Try to do the same problems again, because some of them may not be that obvious when you start doing them yourself. So I'll just stop at this stage of the section, and I will continue with this section, of course, next week on Tuesday. And now I'd like to do a little problem, a nice problem for you, and then give you a quiz similar to this exercise. So I just saw a nice problem like exercise number 3 that talks about a coin and a die. So what you do is you look at the probability of getting outcome of tails and 3 when coin is tossed and a die is rolled. So what is going on here? Well, you have a coin, head or tail. There are two possibilities, right? And for the die, for that little cube, remember we already worked with it, there are 6 sides in it, right? We have 6 choices. So you can have either 1 or 2 or 3 or 4 or 5 or 6. So what they are interested in is to get a probability that someone gets a tail for the first and that someone gets 3 on the second. So what would be the answer? Well, for the first one, for the coin, out of 2 choices, right? There are 2 choices here. I have only 1 tail, this one, right? 1 out of 2. And then for the die, out of 6 choices, I have only 1 3. So it's 1 out of 6. So if you multiply these 2, you get 1, and 2 times 6 is 12. So this is my percent. Right. So probability of tail and then 3. So I can ask you something similar. What's the probability that you get a head and 6? So can you calculate for me for the quiz the probability to get head and 6 on the same exact experiment? And the hint is look above, look above. It'd be pretty much the same thing, right? So that's our quiz for today.
I'm sorry, Professor, you said number 5?
The exercise is number 3. But you need to find probability of head and 6. Same as exercise number 3, but different, little bit different question. Exercise 3 setting, not 5. Bye-bye, have a great day. Bye-bye. Have a great day and have a good weekend. Thank you so much for coming over. Bye-bye.